Omkar, you are now the host. You can start. Okay.
Yes, sir. Yeah. So am I audible to everyone?
Yes, sir.
Okay. Let's wait for 5 minutes, then I'll start. So actually there are a couple of students who are yet to submit assignment number 1. So I mean, did anyone face any issue while uploading the assignment on Google Classroom?
No, sir.
No, sir.
At least, no, sir.
No, right?
No, I think.
Okay.
Sir, can you tell us which students are yet to submit?
So it would be better if you can tell us.
Then we will, yes, sir, we can coordinate.
So are you able to see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Uh, Sorry, just a second. Hello. Hello. नहीं नहीं हाँ. Okay, so let's start. Did you guys go through topological sorting?
Sir, could it be possible for you to start with the 2 endpoint problem first?
Which problem?
The counting the number of fake coins in 2 end problems, the assignment problem.
The fourth
Oh.
problem.
Okay, okay. So, is this a doubt for everyone?
Yes, sir.
Okay.
Yes.
Actually, as of right now, I won't be able to discuss that question. But how about we start the next tutorial with that question? Would it be fine?
Yes, sir.
Yes, sir.
We
Okay,
can
sir.
take it up in the next tutorial because actually I need to cover some portion. So after that, we'll definitely take it up in the next tutorial. Is that fine?
Yes, sir.
Yes, sir.
Okay. Yeah. So did you guys go through topological sorting?
Yes, sir.
Okay.
Yes, sir.
Right. So basically, the motivation behind topological sorting is as follows. You have a bunch of tasks and there are dependencies among them. So for instance, you won't be able to complete a given task unless you have completed all the tasks that depend. Basically, you won't be able to complete a task unless you have completed all those tasks, which are its prerequisites in some sense. Okay, so obviously our objective would be to schedule the tasks in such a way that before we can start a given task, we would have completed all its prerequisites.
Yes, sir.
So that's the motivation behind topological sorting. So how do we model it using graphs?
Sir, we put the tasks as vertices and we send a directed path from the earlier task to the later task.
Okay, so it doesn't have to be a directed path. It should be a directed edge, right?
Yeah, a directed edge.
Yeah. So the vertices are the tasks. And given any two tasks, say I and j, we'll add an edge directed from I into j if I is a prerequisite for j. Okay. So in topological sorting, we want to output an ordering of the vertices such that given any vertex, all its prerequisites appear before it in that ordering. Okay.
Yes.
Right.
Sir,
So,
we can, sir, hello. We
yeah,
can also have some undirected edges, right? For the tasks which don't have a relationship.
I mean, why would you want to include undirected edges, right? Because if there is no dependency among two tasks, then no matter how it doesn't really matter how you schedule them. They can be performed independently.
Yes, I mean, for example, if we have say A points to B points to C and D points to E points to F, then and we introduce undirected edges between A and D, then we can just perform one search and have the entire list. Otherwise, we have to perform two searches and then combine the two.
No. A single search would be sufficient, right? You won't have to perform two explicit searches.
Because there are two disconnected parts.
Yeah, so
but-
what breadth first search will do, it'll any breadth first search or depth first search, what will it do? It'll explore one component, and then it's in the procedure to figure out whether there is a vertex which is yet to be visited. And of course, if it's in a different component, it will not be visited, right? So
Okay,
it will
yes, sir.
automatically switch to that vertex and explore that component. So
Yes.
a single run of breadth first search or depth first search would be sufficient. Okay. Yeah.
Yes, sir.
Right. So can you tell me an algorithm for topological sorting?
Yes, sir. So I was thinking of using BFS.
Okay.
And so after doing BFS, we have a tree, and what we can, sir? So you're saying something?
No, go ahead.
So what we can do is that we can partition the tree into paths.
Okay.
Like, so we can start with the longest path and separate the vertices and all the vertices there, and we have smaller trees. Then we can work on the smaller components, and finally we can use the merge function from the merge sort, so that we are combining the different smaller paths, and in that way we will have the topological sort.
Okay, I think it's quite complicated. Would it be linear time?
No, sir. Yeah, it would not be linear time.
Okay. So your procedure might work, but I mean, I'll have to think about it a little bit, but I think it's a little complicated. You can come up with a very simple procedure for topological sort. So, okay, you are given a directed acyclic graph. So I hope it is clear that the graph should be acyclic. Okay, otherwise you won't be able to complete any task which participates in a cycle. So the graph should be acyclic. It's directed. So it's a directed acyclic graph. Now, first of all, tell me, suppose G is a DAG. Will G contain a vertex of in degree 0?
Yes, sir.
Why?
The first one.
Sorry?
Sir, so after we, so okay. So after we topologically sort some array, so the first one will have this property. Oh, sorry, sir.
So actually you have assumed the existence and only then can you
Right, sir. Right.
topologically
Sorry.
sort.
Yeah.
So
No, sir, because we have already assumed the acyclicity, right?
yeah.
So if you don't have, let's say, so if there is no vertex, whose in degree is 0, then inductively we will have a cycle, right? Like we can,
Right.
if we construct, like we can construct, you can. So let us say there is a vertex v1 which has some non-zero in degree. Then go back to its parent. Like go to the parent. It will also have by our inductive argument, it will also have a non-zero in degree. So we go on, but we have finite number of vertices, right?
Right.
So I think the acyclicity will, together with this argument, will like force one of the vertices to have a 0 integrity.
Yes, yes, that's correct. So did everyone understand?
Yes, sir.
Okay. So let me repeat the argument. You start, let's assume to the contrary that every vertex has in degree at least 1. So you start with any vertex, and now you simply trace a backward path starting from that vertex. So you start with V1. So since its in degree is at least 1, there's going to be at least one edge in the graph that has, which is directed into V1. So you move to the endpoint of that edge. Let's call it V2. So let's call it V2. Again, since its in degree is at least 1, there's going to be at least one edge in the graph which is directed into V2. So you move to the endpoint of that edge, and then you continue this process. Now, since the graph is finite, you cannot continue this process for an infinite number of steps. At some point, you are going to end up with a vertex. You will end up with a vertex whose in degree would be at least 1. So there's going to be an edge which is directed into, say, Vn, but it has to be from one of the nodes that you have already seen. Okay, so that's going to complete a cycle.
Yes.
Okay, right. So that would be a contradiction. Therefore, G always contains a vertex of in degree 0. Now, so with this in hand, now let V be a vertex of in degree 0 in G. Now, is G minus V still a DAG?
No, sir.
Why not?
We can just construct a triangle where everything points to everything and then attach a bonus.
It will still remain in, sir, I mean,
Sorry, could you please come again?
no, sir, no, sir. I think I'm wrong.
It will continue to remain a DAG, right? Because deletion of a vertex is not going to introduce any cycles in the graph.
Right, sir. So
Yes, sir. Right.
it will remain
Yes, sir.
Right?
the deleted cycle, right?
So it's going to be a DAG. Now, so using these two facts, can you come up with a procedure for topological sorting?
So we keep popping the vertex in degree 0.
Popping or deleting?
Deleting. I mean, popping in, attaching it to the list.
Oh, okay. Yeah, that's correct. So that will give you a topological order. So the idea is to find, yeah.
So all the vertex with in degree 0 are not comparable. So that's the
Yeah, that's the whole idea. That if the in degree of a vertex is 0, that means there is no prerequisite task for that particular task. So you can schedule all of them independently. That's the whole idea. Okay.
yes, sir. Right.
So find a vertex of in degree 0, delete it from G, and then you repeat. Continue this process. Okay. So I hope that the correctness of this algorithm is clear. It follows from these two facts. Okay. So since G is a directed acyclic graph, it definitely has a vertex of in degree 0. You simply delete it. After deletion, you will still be left with a DAG, and and by this claim, the first one, we know that it definitely should have a vertex of in degree 0. So you delete it and you continue this process. Okay.
Yes, sir.
Right. So now this is one idea of coming up with a topologically sorted order. Now, this can be implemented in linear time.
Sir, what do you mean by linear time? I mean, is it like some function or some linear function of? Yeah. Okay.
So by linear time, whenever we are talking about graphs, by linear time, I mean linear in the size of the input. Okay.
Okay, sir.
In V plus C time. How? That is something that I'll leave for you to think. Okay. You can very nicely implement this idea in linear time. Now
Okay,
there
sir.
is,
We'll try.
yeah, try this. Now there is another way of coming up with a topologically sorted order, which is using depth first search. So can you think about a way of coming up with a topologically sorted order using DFS? By the way, it will be just a single run of the DFS. Okay. So it will be in linear time.
Sir, we will have to retrace flip the DFS sequence, right?
Could you elaborate a little? Flip the DFS sequence, hasn't?
I mean, we search the graph using DFS, we get a stack. We get a list of vertices, and then we just flip it.
Okay, so you basically mean reverse the order in which the vertices of the graph are explored. Something in that sort?
Yes, sir.
Okay, so that's correct. So, okay, so the algorithm is simply the following. So run DFS on G, and each time DFS finishes exploring a vertex V, add it in the front of your topological order. Okay. Now, when I say finishes exploring, I mean DFS has completed visiting every vertex in the graph which is reachable from V. So you can think of it as the point when BFS will pop V off the stack. Okay.
Yes, sir.
So maybe let me take up an example.
Sir, we must also introduce a condition, right? That if it finds a cycle, it claims that is impossible.
Yeah, but I mean, we have assumed the graph to be a DAG. Okay, so G is a DAG. So in that case, it won't find any cycles. Okay, remember that topological sorting is possible only in case of DAGs, not for general graphs.
Yes, sir.
Okay, so here we have implicitly assumed that the input graph is a directed acyclic graph. Fine. So let me take an example. So let us suppose that BFS starts from here. Okay, so let's say it visits the node B, subsequently it visits D, then it visits E. Now, when DFS reaches E, it has nothing more to visit any further, right? So that means DFS has completed exploring E. So it will output E. So we'll write down E. Next, it's going to backtrack and go back to the node D. Now from D, it will visit C. Now from C, it can visit E. But since E has already been explored by DFS, it won't visit the node E again. So at this point, DFS has completed exploring C. So it's going to output C and we'll write C over here. So that is, we'll prepend C to this list. And then it's going to backtrack to D. Now from D, there is nothing more to explore. E has already been visited by DFS. C has also been visited. So it's going to output D and it's going to prepend it to this list. Then it's going to backtrack and go back to B. Now again from B, there is nothing more to explore. So it's going to return B and we will append it in front of the list. Then it's going to go back to A. Now from A, you can only visit C, but again, since C has already been visited by DFS, there is nothing more for it to explore any further starting from A. So it's going to return A and we'll simply prepend it to the list. Okay, so this is going to be my topological order. Is this clear to everyone how the algorithm is working?
Yes, sir. Clear.
Yes, sir.
To everyone?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So if it's clear, now, of course, we need to show that this algorithm is correct. Okay. So the proof of correctness. So what the claim is, the procedure correctly, or well, not correctly. So the procedure outputs a topologically sorted ordering of the vertices of G. So essentially what we have to show is, given any edge I comma j, so okay, so given any edge directed from I to j, we need to show that I will always appear before j in the ordering. If this happens, then we would have essentially proved this claim, right?
Could you please repeat?
See, we want to show that the ordering produced by this procedure is topologically sorted. It means given any edge, say I comma j, which is directed from I into j, we need to show that this algorithm, that the ordering in the ordering produced by this algorithm, I will always occur before j,
Yes, sir.
right?
Yes, sir.
So to show that for any edge ij, the ordering, so or I will appear before j in the ordering output by the algorithm. So how can we go about with it?
So we try to show that in the DFS it will appear later. It will be popped from the stack later.
Okay, right. But
There cannot be a directed path from I to J. So if there
As
is a
long as
directed path,
yeah, go ahead.
as long as all the paths from I are all the vertices reachable from I are not popped from the stack, I will not be popped. So it is still in the stack. So that means that we are popping J before I. So in the topological sorting, in the list that we are creating, J will appear after I.
Okay. So what you're saying is correct if DFS visits I first. But it is also possible that DFS might visit J first. In that case,
but DFS cannot visit I from J because the graph is acyclic.
yeah, it cannot visit I from J. That's correct. So what's going to happen in that case?
So that's why J will always appear after I, right?
J will,
from I to J, then obviously I will be, I mean, J will be after I.
Yeah.
So I mean, DFS works like this.
Yes, that's correct. Okay. So we have two cases to consider. So I'm just summarizing whatever you have said. So case one is DFS.
Sir, what have you written in the first line? The first
this
line.
one, claim.
Yes, sir.
So it basically says that the above procedure outputs
okay.
an ordering which is topologically sorted.
Okay, sir.
So case one is when DFS visits I before J. So if this happens, then it is quite obvious that since there is an edge from I to J, J will be explored first by DFS and subsequently it's going to explore I. So in that case, J comes before, sorry, I comes before J, right? Is this clear?
Yes, sir.
And the second case is when DFS visits J before I. Now, if this happens, then it is certain that I will not be discovered by DFS when it is exploring J. Okay, because if that happens, then you end up creating a cycle in your graph. Right?
Right, sir.
So I will certainly not be discovered when I'm exploring from J. And since I'm exploring, so of course the two nodes will be explored independently. And since I'm exploring from J first and then from I, it is quite obvious that I will be prepended to J in the list, I mean containing J. So essentially I will occur before J. Is the argument clear to everyone?
Yes, sir.
Everyone?
yes, sir.
Yes, sir.
Okay. So the running time of this algorithm is big O of V plus C. So you can come up with a linear time algorithm for topologically sorting the vertices of a directed acyclic graph. All right. So now, did you guys try the questions which were given in the problem set?
Yes, sir.
All the questions?
No, not all the
No,
questions.
sir. Not-
Okay. So which are the ones you did try?
The first one.
Sir, I could try like the first. I could do, but then I don't know. Like second, third, I didn't know how to like start or.
Okay. So, um, okay. So what I'll do is I'll maybe discuss. So actually, if you haven't tried them all, it's really no point discussing all of them. So let's see. I'll not discuss I'll not give complete solutions. I'll maybe point you in which in the direction in which you might want to think about those questions. Right. So let's start with the first question. So was anyone able to solve the first question?
Yes, sir.
Yes.
Yeah. How did you do it?
Sir, we do BFS with alternating colors, and if at any point we find that there are clash of two colors, then it's not a bipartite graph.
Yeah, that's correct. So what we do is, so you are given a graph G equal to V comma E. It's simple and connected. So we'll pick arbitrarily any vertex of this graph as the source vertex and run BFS from that vertex. Okay. Now you guys know that BFS explores the vertices of the graph in layers, right? So the first layer will contain the source vertex. The second layer consists of all the neighbors of S. This is layer 2, so L2, L1. Then the third layer consists of all those vertices which are adjacent to some vertex in L2 and haven't already been visited by BFS. So that will be L3 and so on and so forth, right?
Yes, sir.
It's just the way BFS works. Okay. You start with the source vertex. So it's going in layer 1. In layer 2, you will have all the neighbors of S. In layer 3 consists of all those vertices which are adjacent to some vertex in L2, but haven't already been seen before. Okay. So this way, BFS essentially traverses the entire graph. Now, based on these layers, we are going to assign labels to each and every vertex. So this is actually very similar to the coloring analogy that you are giving. What we'll do is we will color every vertex which belongs to a layer indexed by an odd number with, say, blue color, and we'll color every vertex which belongs to a layer indexed by an even number with, say, green color or red color. Okay.
Could you please repeat?
Yeah. So did you understand this, that BFS visits the vertices of the graph in layers?
Yes, sir.
Right. So what we are going to do is we'll color S1 with blue. Then we will color every vertex in the layer L2 by red color. Then we'll color every vertex in the layer L3 with blue color. Then again, we'll color every vertex which belongs to the layer L4 with red color. And so on. Sorry? Sorry, did anyone have any question?
No, sir, it's fine.
Okay. So you continue doing so. And now, once you have colored every vertex with either red or blue, now you simply scan the adjacency list and identify whether any two vertices which received the same color are adjacent to each other or not. Okay.
Right, sir.
So now can you tell me why this works? Let's say the graph is bipartite.
And
Why
it
will
doesn't
this
have any odd cycles.
Right, sir.
It has no odd cycles. Okay. So, I mean, why would this procedure work?
Sir, if any two different color vertices are adjacent, then we have odd cycle.
No, there can be an edge between vertices which receive different colors.
I mean, the same cycle.
Same.
Color.
Exactly.
Yes, a
Right.
neighbor should be in different partites. We can
Yes, that's
that.
correct. So basically, you should see that if we assume without loss of generality for S to be in V1, then the subset of vertices which belong to the layer L2 are in V2. Similarly, the set of vertices which belong to the layer L3 must be contained in V1 if the graph is bipartite. Okay. Similarly, the set of vertices which belong to the layer L4 will be contained in V2 and so on and so forth. So the exploration is of your graph is essentially alternating between V1 and V2. Right now, since the graph is, so this is because the graph is bipartite. Okay, this we are alternating between V1 and V2 while exploring the graph because the graph is bipartite. We have assumed the graph to be bipartite. Right. So now, since each bipartition is expected to be an independent set, there should not be an edge between any two nodes over here or over here. Okay. Or as said before, you can also argue that it will create an odd cycle if such a situation occurs. Okay. So is the algorithm clear?
Sir, in the exam, sir, in problems like this, should we give a proof of correctness?
Sorry?
So I mean, in
Sir,
problems,
in exams, if we are asked to find an argument, do we have to provide proof of correctness, runtime, all of this?
Yeah, so you can give this argument.
okay, sir.
Okay. Now, by the way, how will you find the odd cycle? Let's say I tell you that the graph is not bipartite. So that means you have found a pair of vertices which have received the same color and are adjacent. Given this, how will you find the odd cycle?
Sir, during the BFS process, we are constantly checking if the vertices are gray or not, right? So we will be probably hit a same color vertex. So
Could you come again? I didn't get it.
In the BFS process, we are while exploring, we convert. Whenever a vertex is explored, we convert its color from gray to something, gray to blue, and if we reach a vertex that is already colored blue, then we do not consider it. So we can do the same thing. Only here, if the color is same, then we claim that that's the odd cycle, and if it's not, we keep going.
Okay. For BFS, yeah, but actually that will tell you that that will tell you that there is an edge between two nodes that have received the same color. That how will you essentially output the cycle? I think somebody else was saying something.
Sir, can you please repeat the question? I mean, what are we trying to find out?
So see, if you are able to find two vertices with the same color which are adjacent to each other, then you have basically figured out that it is not bipartite. Okay. Right now, of course, if the graph is not bipartite, it contains an odd cycle.
Right.
We want to find that odd cycle. So what we could do is simply find the least common ancestor for the two vertices. Right? See,
Yes, sir.
BFS
Yes.
gives you a BFS tree, right? It gives you a tree. So now you simply retrace your steps back until you find a ancestor which is common to both. Is it clear to everyone?
Sir, what would be the algorithm?
Yes, so the idea is clear, but like how will we implement this?
The algorithm and the timing.
Correct. Yes, sir. How will we implement this?
See, when you run BFS, you will end up with a BFS tree, right? You can, so basically, it's very easy to come up with a BFS tree. All you need to record is the, in some sense, the parent pointers. So though for every vertex, so the moment BFS, so the moment, so let's say you have an edge UV, the moment BFS discovers the vertex V by following this edge UV, what you can do is you can store U as the parent of V in an auxiliary array. You create another array indexed by each vertex, and you essentially store the parents.
Okay.
Right? And then, so once you have figured out the vertices, once you have figured out these vertices with the same color, all you need to do is now retrace your steps back by following parent pointers, which you have already stored when you run your BFS procedure, when you did your BFS procedure. So that's going to take order of E time.
Sir, but in an array, let's say when we are storing a binary tree, then let's, for example, just say we did an implementation of heap, like we had like the child at 2i and 2i plus 1 positions, like so. Sir, but here, sir, the number of children are not fixed. It's going to vary. So in an array, how are we going to like implement this? Like like I'm just trying to get ideas. Like how are we trying to get trying to generate that tree structure in an array? Like the parent preserving the parent-child relationship and accessing it in constant time. Like finding out. Yes, sir.
So, sir, is what we are creating similar to? I mean, we list all the vertices, and then for every vertex we attach its parents in another list that's hanging from that vertex, right?
Essentially, we are creating a linked list, right?
I mean, you can create a linked list or even an array. It doesn't really matter. See, every child is going to have a single parent, right? It's not going to have multiple parents. So it wouldn't really make sense to maintain a list of parents. All we need to keep track is of the parent pointers. If I know the, so not parent pointers, but parents in general. If I can keep track of the parents, then what I'll do is, suppose I want to retrace a path back to my root, what I'll do is I'll see what my parent is.
So
then
if I have an array
to
like
that vertex, I'll again see what the parent of my parent is, and then continue it.
Okay, so sir, if we have like an array, if we have an array 1 to n, we label the vertices 1 to n, and then we have another like a parent, like parent key type array, again 1 to n. So for let's say vertex 3, at the second array we will store its parent index maybe. or something like that.
You don't really need two arrays, right? You can index your array with the labels of your vertices.
Oh, okay.
And then you, for each vertex, you simply place the index of the parent, of its parent.
Oh, yes. Okay. Yes, sir. Yes, got it.
Right?
Yes, sir.
So by retracing your steps back, you simply find the least common ancestor, and then you would have essentially found your cycle, odd cycle. Okay.
Yes, yes, I got it.
Got it?
So yes, sir. So we are making a BFS, and on layer I, we find a vertex that is not the color that it was supposed to be color of. So that vertex must have more than one parent, and one parent would be the parents from the previous layer, and one parent would be some other parent that we have used the color of. So we go to the parents of the two parents and finally found a common ancestor, and we have a cycle.
See, in the BFS tree, you cannot have two parents, right? Otherwise, you would end up with a cycle. See, you won't have two parents. You simply need to record that. You will so see how we have defined which parents are we talking about is. Now, of course, you could have multiple edges in the graph which are incident to you. So let's focus on you. And let's say V1, V2, V3 are its neighbors. So suppose I want to record the parent of U. Now, which one of V1, V2, and V3 should I be recording? So it should be that one which was used by BFS to reach U. I mean, so if BFS it visits V3, and if it uses this edge UV3 to visit U for the first time, then we'll record V3 as the parent of U. Okay? Does that make sense?
Yes, sir. Makes sense.
So is it clear to the person who asked the question?
Yes, sir.
Okay.
Sir,
So yeah.
Detecting a cycle. Sir, will this be order n operations?
Yeah, it'll be order and
Order n.
operation.
Yes, sir.
Yeah. Okay.
Sir, could you please repeat one thing? That suppose we are starting from some source is, and then in the layer 2, suppose there are 2 points, say A and B, which are actually connected.
Okay.
I mean, there's an edge between A and B. Then and maybe okay. So then I mean, could you please explain? I mean, what should we do next in order to find whether? I mean, okay. So the previous question, the previous problem that we were discussing is that whether a graph is bipartite or not, right?
Yeah.
Or we were trying to detect a cycle, odd cycle.
No. See, our original question was to figure out whether the graph is bipartite or not.
Right.
Now, once we have determined, now if the graph is bipartite, well and good. Now, if the graph is not bipartite, then it definitely contains an odd cycle.
Right.
So now we were basically discussing how we would find that odd cycle.
Okay, right.
So in order to find that odd cycle, we took recourse to our BFS tree. So in the BFS tree, so basically, when we would when we would have detected that our graph is not bipartite, that would happen when we would have found a pair of vertices, say u comma v, which received the same color and still were adjacent to each other.
Right.
When that happened, we said that the graph cannot be bipartite.
Right, sir.
So now I want to find an odd cycle. So what I'm going to do is I'm going to take help of my BFS tree to find the least common ancestor of u and v in that tree.
So this is after detecting these 2 points u and v, right?
Okay. So
Sir?
yes, that is.
This is after detect. So whatever we shall do next is after detecting these 2 points u and v, right? Okay, so then we are retracing from
Yes.
retracing back from in that BFS tree, right?
Hello, sir. You are not audible.
Okay. So
Sorry, you were not audible for a few seconds.
okay. Am I audible now?
Yes, sir.
Okay. So right. So is this clear now?
Right, sir. It's fine.
Yes, sir. Fine.
Okay. Since we are running out. So let's take up the next question.
Sir, before the
Yeah.
next question, hello.
Yeah.
Sir, you said that there was a method of removing the in degree zero vertex and doing topological sort in that way.
In which question?
Sir, in topological sort.
Okay.
Sir,
Yeah.
so can we run DFS on the with the detection of the directed edges flipped? Then we pick a V, we travel upstream, and we pop the final vertex from the stack, and then come back. That will be doing that algorithm. So it's DFS running on the let's say the mirror version of the graph.
Oh, so okay. Yeah, that will also work.
So
It should work.
So it would be linear time algorithm. So is that the algorithm that we're talking about?
No. The algorithm that. Sorry.
Sir, can you please repeat his argument? I mean, the argument he just gave.
So for this
Using
topological sorting.
Sir, the argument he gave using in degree zero.
Yeah. So what he's saying is that, so here what we was talking about, we said that in each iteration, we'll remove a vertex with in degree zero. The resulting graph will be a DAG. We'll again remove it. So it should contain a vertex of in degree zero. We'll remove it and continue this process. So our objective then reduces to finding a vertex of in degree zero, right? So now what you could do is that instead of working directly with the original graph, you could simply reverse the direction of each edge in the graph and then run BFS from the DFS from the the sink of the original graph.
Okay, sir, I got it.
Okay.
Yes, sir.
Yeah. So the last vertex that you will visit will actually be the vertex of in degree zero.
Right. Right.
But then, okay, then there is, I think, this one thing that each time you delete a vertex, you will need to invoke a DFS.
Sir, no, sir. Sir, run the DFS from E using the opposite rights, and you will find that this is the same sequence that.
Yeah.
Because every time you finish a DFS, that would be the vertex of in degree zero. and then you
Right.
will do that and come back one step, and then you continue. It's the same as BFS.
Oh,
only with the
okay,
arrows.
okay. I miss. Okay, yeah. Got it. Yeah. Fine.
Sir, but this is not the implementation that you were talking about.
No, I had a different one in mind. It uses, well, it can, so basically a single scan through the adjacency list of the matrix would be sufficient to do the topological sorting. You can, so in a very clever way, using some suitable data structure, you can actually come up with a linear algorithm for which would involve a single scan to the adjacency list of the graph. So think about it, but what you're saying also seems correct. So, right. So let's discuss the second question. So just like give me a minute, I'll read the question. Okay, so did anyone try question number 2?
Yes, sir. So basically, what we have is we have a problem where we have a directed graph, let's say G equal to V comma E, and we have a fixed vertex, let's call it T, because we have a town hall vertex, let's T. So what we need to show is that for all V, small v belonging to the capital V set, there is a path from V to T, right?
Yeah, if at all there is a path from S to V, then there's a path from V to T as well. That's what we want to show.
So basically, the question is like from any point, there is a legal path to T. So basically, for all V belonging to, so for every vertex, there should be a path from V to T, right?
No. So it basically says that suppose so it says no matter where you reach, there is always a way to drive back legally to the town. Okay. Yeah. In
So,
some sense, that's what it's.
So no matter at which straight point you are, let's say if we are like talking about straight points, let's say point 1, point 2. So there must be a path from that legal path along the one ways to T. So there must be a path from every vertex, like let's say from small v to that vertex T, right?
Right.
No, I mean, T should only be a part of directed cycles. I mean, there could be paths which are not points which are not reachable from T at all.
Yeah, it is possible. So in that case, you simply output a no. Or so that is one option, or you could simply talk about those paths. I mean, you could talk about paths from vertices which are reachable from T to T.
Yes.
You get my point?
Yeah, I mean, say there are 4 points, and from 2 of them you can reach T, and for V1 and V2 you can reach V1, V2 from T, and T from V1, V2. But V3, V4 are unreachable from T. So there doesn't need to be any path from V3 and V4 to T.
Right. Right. So that's what we are. So did you get the question? So
yes, I got it.
we'll be talking only about those vertices which are reachable from T.
Okay.
So how do you think you can go about with it?
So then we might
Should we consider some back edges in the BFS tree? Like, I mean, back edges from the leaves.
But you may consider back edges, but then the then actually you would have to run BFS multiple times, I guess. Well, not necessarily multiple times, but
Sir, suppose we
if the
we start. So suppose we start from the town hall. So let's call it S or maybe T, and we perform BFS, and so we get a BFS tree, and we get a BFS tree, and so we are considering only the leaves. Okay, so if there is so now obviously all the leaves must be okay. No, I guess there's a problem here.
see, there could be actually multiple cycles. The number of cycles could be very large. So I don't think it will be feasible.
Sir, all we need to find is that all leaves lead back to A, right?
Yeah.
Right.
But it would
Your
also,
friends-
but it would involve
Sorry?
more vertices. I mean, when we are finding the path from a leaf back to A, it will involve vertices which are not in the BFS tree, but in the graph, right? So it will involve even more vertices.
Yes.
So maybe we do a DFS and find out if every DFS loop reaches back to A.
So so basically for what you're saying is for every vertex which is reachable from T, you run a DFS with that vertex as the source.
But that would not be linear time. That will be
No, that
Yes,
won't
sir.
be linear time.
Yes, sir. That was okay. So that was the problem. It will not be linear time. But how do we get a linear time?
Yeah.
That was my initial confusion also. Although I thought it in a different way, but my problem was from V to T. From if I have to from multiple vertices, V1, V2, V3. If we want to find out if there is a path from V1 to T, V2 to T, then how to get a linear time there?
Yeah. Yes. So how do you think can this be done?
Sir, there must be some. I don't know. Will there be a connection between the paths? Like if so, it cannot be. Okay, so if there is, let's say, from V1 to T, I'm going, and if let's say from V2 to T and V3 to T, if there was no connection between these three, then obviously we cannot get it in linear time. So there must be, I don't know.
No, there doesn't necessarily have to be any kind of connection between these paths, right? I mean,
yeah.
Sir, hello.
Yeah.
Sir, we can do a DFS every time it reaches a new vertex. We color it something, say green, and every time, and if we find that in the path, after we go through the path, if we find that the path does not end in A, we claim that we claim that, whoever claimed that town hall is always reachable is lying. And if it is reachable from A, we color it green, and then we just keep a list of whichever vertices are hitting during the DFS algorithm, whichever are hitting a green vertex.
No, but that will ensure reachability from the town hall. I want reachability to the town hall, right?
Yeah, I mean, all the green vertices are vertices which have a path to the town hall.
But then how will you identify such vertices?
We will run the DFS and it will reach a point A. It will reach A.
What will be the source of your DFS?
Source will be A, but during the algorithm, we will find that because we are during the DFS algorithm, we search all the edges, right? So at some point, during the DFS, at some point, we will probably loop back to A. If we don't, then it's done. If we do, then we mark all the vertices in that point green. Because
wait. Just a second. So what is your A first of all? Is it the town hall?
Yeah, source is town hall A.
So A is my town hall vertex.
Yes.
Right. Okay,
Yeah.
now I run DFS from town hall.
Town hall.
Yeah,
We
then
we check if the DFS loops back to A.
okay.
If it does not, then then it is immediately done. If it does, then we color all the vertices that we reached in that loop green, and then we keep doing it. And if at any point in time, let's say A is also colored green, if any point in time during the DFS we fail to reach a green vertex, then it's false. The claim is false.
Yeah, so the problem over here is that you need to go through a lot of cycles. What you are essentially trying to identify is cycles, right?
So just one DFS will do, right?
Yeah, one DFS will do, but then
So it's a linear time.
yeah, but you are not simply doing that DFS, right? You are also again retracing your cycles, because as you said, you will be coloring each vertex which is on the cycle as green. And you could have multiple such cycles. For example, if I have a complete graph, then any subset of at least 3 vertices is going to end up in a cycle.
Yeah.
So
okay, so then we just color the last one green, and maybe that will okay.
So actually your friend just gave a solution to this problem in this when we were discussing topological sorting just now. What if instead of working with the original graph, we were to reverse the direction of every edge in the graph and run DFS from the source, from the town hall?
Sir, could you please repeat?
See, instead of working with the original graph G, what if we were to reverse the direction of every edge on the graph and then run BFS starting from the town hall?
Okay.
So okay. So G is your original graph. G dash is obtained by reversing the direction of every edge in G. Right? Now, if I run BFS from S in G dash, and let A be the set of all vertices which are reachable from S in G dash. Okay, so A is the set of all V in VG dash such that there exists a path from S to V in G dash. Does this imply that there exists a path from V to S in G?
Yes, sir.
Yes, sir.
Yes, sir. This is exactly the same.
So aren't we really done here?
Sir, but then we will also have to show that every single V in capital A is reachable from the town hall in original G.
Yeah, so that is one thing that you'll have to first figure out. You'll first have to identify the subset of vertices which are reachable from the town hall in the original graph. And
okay, so we run a linear time algorithm to reduce the number of vertices, and then we reverse and run again a linear time algorithm.
Yeah.
Okay. Yeah. That.
Okay, and then you simply need to compare the lists whether everyone is there or not.
But list comparison is square time, right?
I mean, it can be done in a. You will get an extra overhead of log if you label the vertices as integers.
So we don't need to compare the lists. We, in one linear time, we reduce the set of vertices to only those which are reachable. And then in the next linear time, so we add 2 linear times, so we get linear.
Yeah, but if you want to check whether there is a path from every vertex which is reachable from S, so suppose there is a vertex which is reachable from the town hall in the original graph. it might be possible that there might not be any path from that vertex to the town hall, right?
Yeah, so
Makes sense?
I mean that will okay, so that will not be included in G dash.
Yeah. So,
Sir, but again, list comparison will involve more time.
yeah, so that will be a little, that will be the overhead that you will encounter, but that if you are a little careful, it's really logarithmic if you label the vertices if you label the vertices as integers.
Sir, but we have to find a linear time algorithm. The problem, right?
Yeah, it's a linear time. So see, then in that case, yeah, so then in that case, you would actually have to avoid the comparison of lists. I didn't check the linear time. Okay. You'll have to avoid the comparison of lists. So you can actually simply assume that you want to find whether every vertex has a path to S, something of that sort. Okay, so it's just to avoid that comparison. Otherwise, you will need some extra overhead, of course. Is this clear to everyone? But the main idea is this. That's the important point. Okay.
Yes, sir.
Is it clear to everyone?
Yes, sir.
Yes, sir.
Sir, so is this
Yeah.
problem actually not possible in linear time? The finding of directed loops?
Finding of directed loops.
Yes, sir. Every point visitable from T is also, we can also find a path to T. So it's a loop, right? So
Yeah.
we are finding directed loops. Is that
Yeah.
not possible in linear time?
No. So if you think that a single run of BFS is going to help you out, that won't be possible. The reason is that you might end up with a lot of cycles. So you will have to retrace, for each cycle, you will need to figure out whether it, goes back all the way back to T. And you might have some other cycles as well, which involve T. So it won't be a linear time, because if there are a lot of cycles, then checking those cycles is going to be very difficult. In fact, I'll give you this as something to think about. Try to come up with a graph that has a lot of cycles, and a single run of BFS won't work to identify those cycles. I mean, you will get the cycles, but in order to actually find those cycles, see, presence of a back edge definitely indicates that there's going to be a cycle in the graph. But if you want to actually output that cycle, or if you want to test some property of that cycle, you need to trace that cycle. And that won't be an easy job if you have a lot of cycles in your graph. Does that make sense? Try to think about such graphs. Yes, no, maybe.
Yeah, yes, sir.
Okay. So we are already out of time. So try to solve the remaining problems, question 3, 4, 5, and 6. And let's see, we'll maybe discuss on Classroom or maybe in some other tutorial. Okay?
Yes, sir.
Okay.
Fine. So are there any doubts, any questions in whatever has been covered? in the class, in the tutorial? Do you guys have any suggestions? So how are you finding the pace of the class? Are you able to understand everything?
Yes, sir.
Sir, what about the scores?
Sorry?
What about the scores from the earlier two tests?
The quiz?
Yes, the quiz.
Yeah, so you will get the scores probably by the end of this week, or maybe sometime next week.
Okay, sir.
Yeah.
Yes, I wanted to ask one more thing.
Yeah.
So in the assignment question number 6,
Hmm.
so so can you open question number 6 now? I mean, just
Just a
one
second.
thing.
Just a second.
Sir, is there any information regarding the mode of examination?
Sorry?
Sir, is there any information as of yet regarding the mode of examination?
No, I actually don't have any idea about that. Yeah, so question number 6, that is average running time of a comparison sort.
Yes, sir. So we have to show that there isn't any algorithm whose average runtime is a small o of n log n.
Yeah.
So I was a bit confused regard the question, as like, so insertion sort is a sorting algorithm, comparison based sorting algorithm, whose average runtime is big O of n square.
Yeah.
So I mean, can we claim that this is a small o of n log n?
Yeah, big O of no. See, small O of n log n means that so the question basically asks us, you cannot come up with a sorting algorithm which makes fewer than n log n comparisons. That's what we mean by small O of n log n. Okay,
Oh,
so you cannot say that insertion sort, I mean, that is small O of n log n.
oh, okay, sir. So okay, I understand.
Sir, but we were able to show that we need at least log n factorial many comparisons, which is omega of n log.
Yeah, that's fine.
I mean, that is not small o of n log.
No.
Sir, so I mean, can you please
See,
give us a solution to this problem? I don't think anyone in our class was able to come up with one.
so we'll post the solutions soon for the questions.
Okay.
Yeah.
Okay.
Yes, sir. So the log of n factorial thing is fine. I don't know.
Yeah, that's fine. All right. So let's end the meeting here. Thank you, everyone. And please try the other problems as well. If you have any doubts, questions, feel free to ask on the Google Classroom, or you can also drop mail to one of the TAs. Okay, thank you.
Okay, thank you, sir.
Thank you, sir.
Thank you, sir.